Hello. We're going to get started now. Just a reminder that we have a exam tomorrow, and I sent out a announcement about the exam. The coverage is what did I say? 7.3. 7.4, 7.8. We did not cover 7.5, which is just put more practice problems on 7.1 to 7.4, and then 11.1 to 11.4. So those will be on the exam. I know that some of you have questions on the homework, the most recent homework. I'm going to give you time to ask your questions, but at first I want to continue with what we talked about yesterday for about 45 minutes to 50 minutes, then we can switch to questions that you might have from the homework. Is that okay? All right, I'm not hearing any objections. Let me get started. So just a quick review. In the second half of Monday's lecture, we talk about absolutely and conditionally. So recall a series AN is absolutely convergent if the series with absolute value of AN converges. And the absolute convergence also implies convergence. So if a series is absolutely convergent, then it's definitely convergent. I probably should draw the arrow this way. And also, the series AN is conditionally convergent if the absolute value of AN diverges, but the series itself is convergent. I'm just going to write converges. So that's the difference between absolutely convergent and the conditionally convergent. Here's a few examples. So consider, let's see, determine if the following series are absolutely convergent or conditionally convergent. Or divergent. So the first example I have is the series from 1 to infinity of -1 to n divided by cube root of n. So that's a series given. Well, to know if it's absolutely convergent, we have to take this given series, find the absolute value series from it. So from here, we're going to consider the series with absolute value of -1 to n divided by cube root of n with absolute value, again, n from 1 to infinity, right? So if I add absolute value there, the -1 to the n will always become +1. So we don't have an alternating series. We just have 1 over cube root of n in absolute value sign. But we know n is positive, right? It's 1, 2, 3, 4. Cube root of positive number is always positive, so we can drop the absolute value sign completely. So that's a cube root of n. So that's a n That's a series 1 over n to the 1/3. And from here, we want to know if this is convergent or divergent. Right? We end up simplifying that into a much simpler series, 1 over n to the 1/3. Here, this is the 1 over n to the p. We can use p test. So p series test. And the p is equal to 1/3, which is less than 1. From the p series test, we know that this series at the end is divergent. Well, if that series is divergent using the p series test, that means this absolute value series, this one will also be divergent, right? So the absolute value series is divergent. That's the second part. So that means the series is not going to be absolutely convergent. But is it conditionally convergent? We have to see if this is convergent or not. So let me write down. So the series, the given series, this one, is not absolutely convergent. Because the series with the absolute value of the absolute value series diverges. Well, let's see if it's a given series itself is convergent or not. So this, if you look at the series, this series is alternating, right? Has a -1 to the n. So this is alternating series. And if we want to know if it's convergent or divergent, remember that's like the alternating series test. The first one, we have to take the limit goes to 0. The second condition is that the terms will be decreasing. So check the first condition, I'm going to call it A, which is the limit n goes to infinity bn. So the given series from there, the bn is you put away the -1 to the n. So bn, which is limit n goes to infinity of 1 over cube root of n. So that becomes 1 over cube root of n as n goes to infinity, that goes to 0, which is a good thing. So the first condition is satisfied. How about the second one? The second one, we need bn greater than or equal to bn plus 1. Well, let's find bn minus bn plus 1. So that's 1 over cube root of n minus 1 over cube root of n plus 1. If we common denominator there, so we get cube root of n plus 1, and then we get cube root of n plus 1 minus cube root of n. I hope that you can see it. For n is positive, cube root of n plus 1 is always going to be bigger than cube root of n as n increases, because if n is 5, 5 plus 1 is 6, right? Cube root of 6 is bigger than cube root of 5. So the numerator is always positive. Let me finish this. And then the denominator is always positive. So overall, you get a positive value. Therefore, we got bn greater or equal to bn plus 1. So the alternating series, so the series -1 to the n over cube root of n. This alternating series, the given one, is convergent. But the absolute value of this series is divergent. Therefore, this series, -1 to the n of cube root of n, is conditionally convergent. Okay, so that's how you show it's conditionally convergent or absolutely convergent. So there's a couple of questions. So what are we supposed to do after we determine it's not absolute? So the question is to determine if the given example is absolutely convergent, or conditionally convergent, or divergent, right? So if you determine that it's not absolutely convergent, you have to decide if it's conditionally convergent. If it's not conditionally convergent, then you basically conclude that it's divergent. So you kind of like go through it one at a time. So that's what I did. I find the absolute value series, and I found out that that's divergent. So I know it's not absolutely convergent, but I still need to find out if it's conditionally convergent, which means you have to look at the series itself to determine if it's convergent or not. That's what this work is. To just focus on the series itself. Not all of it, this part. So Chris asked a question, do you know another way to find a Bn greater or equal to Bn plus 1? This is the way that I feel most comfortable with, and the way that I'm familiar with. There might be another way, but I would say don't plug in numbers directly, because for some cases it works when you plug in numbers, but for some examples, when you plug in values, it's not going to give you the correct comparison between two elements. It depends on the value. So I personally don't recommend to plug in numbers directly. Just find the difference, see if it's positive or negative. There might be another way. If you find out another way to do it, you can tell me. I'll share it with everyone.
How was the top part of that one? Like down below, like in the other checks.
Here, this part.
Yeah.
This is just so because I know the series is alternating, you have a -1 to the n, right? So for the alternating series, if you want to find out if it's convergent or not, there's alternating series test, which says the series is convergent if the limit of Bn equals 0 and Bn is greater or equal to Bn plus 1, means that the terms are decreasing. So I did the first part, the first condition, it worked, it's satisfied. Then I say we still have to check the second condition. I probably should say need to check. And that's the work that I did by finding the difference.
I guess I'm just confused on how that negative n to the root third power is positive. Like, how are those two things, the n plus 1 minus the root n, how is that turning positive? Because I see a negative in there.
You have negative, but the difference is positive. That's why I wrote a positive sign. So,
oh, okay.
Yeah, if you think about the cube root function, it looks like this in the first quadrant. Obviously, you have another one down here, but in the first quadrant, if n is here, n plus 1 is here. So if you take the cube root of n plus 1 minus cube root of n, you're going to sort of taking a higher y value minus the lower y value, you get positive difference. So that's what I meant. I meant the numerator is positive after you find the difference. And the denominator is a product of two positive cube roots, so it's just positive. Why don't we use 1/3 and not -1? For part 2, so we need to find a Bn, right? So so Bn if you have a series written in the box that I'm boxing in red, that you can write as sigma -1 to the n times 1 over cube root of n, right? In this form, for alternating series, this part is what we call the Bn. It's a part that you kind of put aside the -1 to the nth power. The remaining part, it's called Bn. So we need to, for the first condition in the alternating series test, we need to take a limit as n goes to infinity of Bn to see if that's a 0. That's why we only use 1 over cube root of n, not -1. Daniel, you have a question? Go ahead.
Yeah, so when we're taking our exam, can we do those little shortcuts you're doing, like at the bottom where it says just positive?
Absolutely. You don't
Okay.
have to find any value, because all we want to know if it's so what we need is that we want to know if the difference is going to be positive or negative, right? That's all we're interested. We don't want to know how big it is. So if you just write positive or negative at the end, it's perfectly fine.
All right, thank you.
Yeah.
Can this sort of question be on the exam, or is this for like next week's quiz?
This is next quiz. So for what I'm talking about now, this is not going to be on the exam tomorrow. And the stuff I'm going to talk about soon is also not going to be on the exam. Any other questions on this? All right, so I have to move on to talk about a little bit more. But I'll give you at least about 15 minutes to ask questions. I know you have questions on the homework. It's not an easy homework assignment. But let me move on to the next part. If you don't have further questions on this absolute convergence. Any final questions on that part? All right, the next section is 11.6. In this part, it's the two tests. They're really easy to understand in terms of the test itself, and also I think it's easy to apply as well. But let me just write down and then give you a few examples. So the first one is called the ratio test. Which says, so consider the series an for n from 1 to infinity. And we're going to take two terms from here. Take the nth term and the n plus 1th term. And then we're going to define a constant L. We're going to define L as the limit n goes to infinity of absolute value an plus 1 over an absolute value. So that's what we call L. Just a limit of absolute value of a ratio between the two last terms. So 1, if L, this L that we defined using the limit, if L is less than 1, then the series an is absolutely convergent. And 2, if L is greater than 1, then the series an is divergent. I should also point out that if the series is absolutely convergent, which means it's also convergent. It's not conditionally convergent, it's just convergent. And the 3, so what if L equals 1? If L equals 1, then we cannot make any conclusion based on this test. We have to apply other tests. So if L equals 1, this ratio test is inconclusive. We need other tests to figure out whether the series converges or not. We need another test. So this is called the ratio test. To apply the ratio test, so you just take the AN and the AN plus 1, find the ratio, put in an absolute value sign, take the limit, and see what you end up with. And that value, L, will tell you whether it's absolutely convergent or divergent, or we don't know. So let me give you an example here. The first example I have is, let me use this example. So the first example I'm going to use is the series n from 1 to infinity of n plus 1 in the numerator to n plus 7 in the denominator. We want to know if this convergent or divergent. If it's convergent, perhaps we can figure out whether it's absolutely convergent or not, right? So I'm going to try to apply this ratio test here. So try with ratio test. So I need the AN and the AN plus 1, right? So I'm just going to write down AN plus AN on the side, which is, this is AN. So that's n plus 1 over 2n plus 7. And the AN plus 1, which is basically take the n, replace it with n plus 1. So that's, so n becomes n plus 1, but then I already add 1 in the numerator, so n plus 1 plus 1. The denominator is 2 times n, now it's 2n plus 1, and then plus 7, right? So that's an AN plus 1. I'm just going to rewrite this, simplify a bit. So that's an n plus 2 over 2n plus 2 plus 7, so that's a 2n plus 9 in the denominator. So that's finding those two terms. And then I'm going to define L, which is limit n goes to infinity of AN plus 1. So absolute value AN plus 1 over AN. So that becomes the limit n goes to infinity. That will be absolute value n plus 2 divided by 2n plus 9 divided by n plus 1 divided by 2n plus 7. It's the fraction is a little bit long, but it's all right. So we're just going to simplify the denominator as a fraction. So we're going to multiply by the reciprocal. So that's a limit n goes to infinity. Absolute value. So for this test, always keep the absolute value sign. So that would be n plus 2 over 2n plus 9 times the reciprocal 2n plus 7, and then n plus 1. And the rest is about try to simplify, try to find the limit. So let me take a quick step. I'm going to expand the numerator and expand the denominator quickly. So the numerator, if I expand it, I get 2n squared. and by foiling, plus 7n plus 4n plus 14. The denominator I have 2n squared plus 9n plus 2n plus 9. I'm going to quickly combine the two terms in the middle, the 7n and the 4n, that give me 11n. Denominator also give me 11n, so plus 14 plus 9. Can anyone tell me what the limit is for this part, for this fraction that we, as n goes to infinity? What is the limit? It's not greater than 1. It's not 16 over 11. It will be 1 exactly. Yep. Good. So both of you are right. So it is 1 at the end, because if you're not sure, we just divide by n squared in numerator and denominator. When we do that, as n goes to infinity, the 11n term, the 14, the 9, they all go away, go to 0. And the leading term, you have 2 over 2, which is 1, right? So here we found out L to be 1. So therefore, L equals 1. Well, based on the ratio test, if L is 1, we don't know if so the ratio test says if L equals 1, the ratio test is inconclusive. So inconclusive. So for this example, if we use the ratio test, we cannot reach a conclusion. We don't know if the given series is convergent or divergent. Therefore, we need to use another test. To find out whether it's convergent or divergent. Now, for this example, this particular example, n from 1 to infinity, n plus 1 divided by 2n plus 7. We can, there's one test that's really easy, which is the first one that you learned, the divergence test. So try divergence test, which is simply taking the limit of an as n goes to infinity, and let's see what that gives you. So if we take the limit of an as n goes to infinity, n plus 1 over 2n plus 7, and someone please tell me what the limit is. It's very similar to this part that we did. Right? So
1 over 2?
1 over 2, exactly. So that is the limit of an. And if you remember, the divergence test says if the limit is not 0, right? Or if the limit is infinity, so divergence test has two parts. So divergence test says if limit an as n goes to infinity is not equal to 0, or if it doesn't exist, the limit doesn't exist, means the limit goes to infinity, then the series is divergent. So here we found out the limit of an that is equal to 1/2, which is not equal to 0. Therefore, the series, the one that we given, n plus 1 over 2n plus 7, is divergent. So this is a good example. I'm sure if you try the divergence test immediately, like before you learn how to before you learn this ratio test, if you just try divergence test at the beginning, you will find out that it's divergent, right? But this example is good because it gives you more tools, like more different, just another test that you can use to test for convergence. Because some other examples, if you try to use a divergence test, you cannot conclude. So you might want to try the ratio test, which actually give you a conclusion. So there's a few tests so far, and depends on the one that you use, and it will some may be inconclusive, some will give you a conclusion. So you kind of have to, play with it and get comfortable with different type of questions. Any questions on this example? So this is an example that the ratio test doesn't give you any conclusion. Then I'm going to give you another example that it may give you a conclusion. Any questions?
So how do you know it's divergent? I know that since it's not equal to 1, or not equal to 0, it has to exist. So is it or less than 1? I mean.
Sorry, you got cut off. I didn't hear the last part. So can you repeat the last part you said?
Is it divergent because it's less than 1?
It's divergent because it's not 0. If it's equal 0, that will be inconclusive. Right? But in this case, the limit is not equal to 0. Then the series is divergent. So if the limit is not 0, or if the limit is infinity or negative infinity, I mean, they're not 0 anyway. So if it's not 0, then the series is divergent. If it's equal 0 from the divergence test, we cannot make any conclusion.
Okay, thank you for clarifying.
Yep. So yeah, so divergence test is important. Make sure you kind of, that will be on the exam. All right, let me give you another example on this ratio test. So the series given is n from 1 to infinity of negative 10 to the n divided by 4 to the 2n times n plus 1. Looks complicated, right? So we want to know, is this convergent or maybe absolutely convergent or divergent? Right, so I'm just going to so Julie, for the I'm not sure which one you talk about when you say inconclusive. Are you talking about the divergence test or talk about the ratio test? For the ratio test, if it's greater than 1, it's divergent. If it's equal to 1, it's inconclusive. That's the ratio test. But for the divergence test, if the limit is not 0, then it's divergent. If it's equal 0, then it's inconclusive. So those two tests have different constants that you compare with. So for this one, again, so the first thing I'm going to do is I'm going to identify. So I'm going to try ratio test. So I'm going to find an, which is negative 10 to n divided by 4 to the 2n. 2n is the exponent of 4 times n plus 1. And then I'm going to find an plus 1. So that will be negative 10 to the n plus 1 divided by 4 raised to the 2 times n plus 1. I'm going to put in that later. And then n plus 1 plus 1. So n plus 1, n plus 1. And I'm going to rewrite this term, just simplify a bit more to make it look better. So this will be negative 10 to the n plus 1. This one is 4 to the 2n plus 2 if we distribute the 2 in the exponent. And the times n plus 2. To make it a little bit easier to, I'll do it later. So anyway, so the next is we're going to define L, which is limit. So define L, which is the limit n goes to infinity absolute value of an plus 1. So that's a negative 10 to the n plus 1 divided by 4 to the 2n plus 2 times n plus 2. And then all divided by the an, which is negative 10 to the n, and divide by 4 to the 2n, n plus 1. So even though it looks complicated, right, there's so many terms in the fraction, but soon most of them will cancel and they give you something simpler. So that will be limit. And the negative 10 to the n plus 1, I'm going to write as negative 10 to the n times negative 10. I hope you're okay with that. And in the denominator, I have 4 to the 2n plus 2. I'm going to write as 4 to the 2n times 4 squared. Right? That's going to break down the exponential term into product of two terms. And I still have n plus 2. So this is just so what I did is I took this part, I took the numerator, I split it into a product. I took 4 to the n plus 2n plus 2, I split it into a product. And remember that I'm dividing by a fraction, right? So I'm going to multiply by the reciprocal immediately, which is 4 to the 2n, n plus 1, and then negative 10 to the n. Why don't we take out negative 1? You don't have to, so because I know that when you multiply by the reciprocal, a lot of it will cancel, so there's no need to take out the negative 1. You could, but it doesn't make a much difference. I just want to kind of cancel things out quickly. So this cancels with negative 10 to the n. 4 to the 2n cancels with 4 to the 2n. I have negative 10, then I have 4 squared. Both are numbers. Then I have n plus 1 and n plus 2. So let me write down. So now I have limit, absolute value, negative 10 divided by 4 squared. That's a negative 10 over 16. Then I have n plus 1, n plus 2. And the n goes to infinity. Right? And it's all in the absolute value sign. So if I take out any constants, for example, this constant, negative 10 over 16, I can move it outside of the absolute value. But if I do that, it will become a positive, right? And I can move it all the way in front of limit. So first of all, I move it outside of the absolute value sign, make it positive. And then I move it outside of limit. So that will become positive 10 over 16 because we move it outside of absolute value, limit, and then n plus 1 divided by n plus 2. And you have a absolute value sign here, but it doesn't matter because the numerator and denominator are positive. So I can just drop it. But you can keep it there, it doesn't make a difference. So that will be 10 over 16. And I'm pretty sure at this point, you know what the limit is for the fraction. It's just 1, right? Because if you take the limit of n plus 1 over n plus 2, it's just 1. And then this will become just 10 over 16, which is a number that's less than 1. Remember, if you remember that for the ratio test, we compare the L with 1. And then we find out that it's less than 1. So since the L we're looking for is less than 1, therefore the series, the given one, is absolutely convergent. And definitely convergent. If it's absolutely convergent, then it's convergent. So that's this example. Any questions on this? So this is an example to show you that, for certain examples, when you apply the ratio test, you can immediately make a conclusion, which is different from the previous example that you cannot make a conclusion, right? So just like all of those tests, when you apply it, it may or may not give you a conclusion, but doesn't mean the test is wrong. It's just not the appropriate test to use. So if you cannot make a conclusion, try with a different one. For examples on the exam, if it asks you to decide if a series is convergent or divergent, let me just digress for a second. So for the exam questions, you have the divergence test you can use. You have the P-series test you can use. You also have the integral test and the comparison test, the two of them. You can use those tests to decide, so you don't have to worry about the ratio test or the alternating series test. But yeah, those are the one that you can try. But anyway, so any questions on the example I just went over, this example? All right, so the next part is the last test that we're going to talk about in this class. So it's not that difficult to apply. It's easy to apply, just like the ratio test. Let me just write it down and go over 1 or 2 examples, and then I will stop there. Yeah. This last test we talk about is called the root test. It's so let me write down. It's good. So this test is good for when you have nth power in the series. I'll show you an example. So but let me write down the test first. The root test has consider the series an for n going from 1 to infinity. And in this time, we don't need 2 terms. We just take the an term. And we're going to define L as limit n goes to infinity of nth root of absolute value of an. So that's how we define the L here. Instead of the ratio, we take the nth root. Or you can write as limit n goes to infinity of absolute value of an raised to the 1 over nth power. Either notation is okay. So just like before, we compare L with 1. So the first one is if L equals 1. Sorry, not equal. If L is less than 1, then the series AN is absolutely convergent. Absolutely convergent. Just like before, just like with the ratio test, the conclusion is the same. It just how you define L is different. In this part, the L is defined as a limit of nth root of absolute value of AN. And the 2, if L is greater than 1, then the series AN is divergent. And the 3, just like before, if L equals 1, this root test is inconclusive. So I would recommend that when you try to look at those tests, put them together, because if one of them makes sense, the other one is a lot easier to understand. The process is the same. You just define an L and then apply it. Try to find the L and then see what the value is. All right, so let me give you one example here. So example. So suppose we have a series from 1 to infinity of 5n minus 3n cubed divided by 7n cubed plus 2 raised to the nth power. So this is what I said in the blue there. So this is good for nth power. So if you have an nth power of that expression, you're adding them together. This is very useful to apply the root test. So we want to know, is this convergent or divergent? So I'm going to apply this test. I'm going to define L, just like the definition says. So define L equals limit n goes to infinity of nth root of absolute value of AN. And the AN in this part is 5n minus 3n cubed divided by 7n cubed plus 2 raised to the n absolute value. Right, it's literally just take AN absolute, add the absolute value sign, and then add the nth root. The next step I'm going to do is because I have nth power, n is it's a positive number, so absolute value of something to the nth power, I can bring the absolute value inside the power n. So I'm going to rewrite it as limit n goes to infinity of nth root. Now this becomes absolute value 5n minus 3n cubed divided by 7n cubed plus 2 absolute value to the n. So basically switch the order of absolute value sign and the nth power. Benefit of doing this is that if we take nth root of nth power, that cancel, give you 1. So that just becomes limit n goes to infinity of absolute value 5n minus 3n cubed divided by 7n cubed plus 2. And from here, it's similar to what we have done before. Now we just have absolute value, which doesn't make much difference. So if you remember that in the past, if we didn't have the absolute value sign, we just divide by the highest term, right? The highest order of n. So here we have n cubed and n cubed, so we divide by n cubed to all terms. That becomes limit n goes to infinity of 5 over n squared minus 3 divided by 7 plus 2 over n cubed, absolute value. Now we can take the limit because the absolute value doesn't make a difference when we take the limit there. So if we take the limit, the absolute value is still there, the 5 over, when we take the limit, this term goes to 0, right? Because the n goes to infinity. This term also goes to 0. We get negative 3 over 7, which is positive 3 over 7. Right? It's just a positive value, but we need to compare this value to 1. So this is less than 1. So since the L here is less than 1, therefore, if you quickly, I know you don't remember this, that's totally normal. If L is less than 1, then the series is absolutely convergent. Therefore, the series, I'm just going to write the given series. This one. Is absolutely convergent. So that's how we use this root test. It works really well for this specific type of questions.
What's the difference between the first and second step? I only really see like the parentheses dropped.
Between the first and the second step, so in the first step, this is an, right? And that's inside the absolute value sign. In the second step, what I did is I sort of take the nth power, I move it outside of the absolute value sign. When I do that, I don't need the parentheses anymore. So that's the first and the second step.
From the second to third step, is that when you just canceled the n?
Correct, with the nth root. Yeah.
Okay.
Is there a name for that? Like just canceling the nth root?
I don't know if that's a name. So basically, so what that is kind of like when we take a square root of, x squared, that just become sort of absolute value of x. That's what we have. You can also think about it's like if you take some expression raised to the nth power, but then you raise to another exponent 1 over n, which is like an nth root. So that multiply those two exponents together, give you 1, just end up with this absolute value part. I don't really remember the name for that. I think it's just one of the properties with exponents. Any other questions on this? So that's 1 is less than 1. Let me give you another quick question. I promise you after this, and then after this example, I'm going to stop. This example, just follow the same idea to use a root test. So this example will give you a series n raised to the nth power divided by 3 to the 1 plus 2n. The 1 plus 2n is the exponent of 3 for n going from 1 to infinity. We want to know if this is convergent or divergent. So I'm going to try to use the root test because I noticed that there's an n as the nth power of n, and also in the denominator they also have an n as the power of as the exponent of 3. So both of them has an n as an exponent. So the first thing I'm going to do is I'm going to take what's given and then rewrite it, make it looks like something raised to the power of n first. So I'm going to take the series n to the n divided by 3 to the 1 plus 2n. I'm going to rewrite this as The numerator is just the same, nothing changes there. The denominator, I'm going to write as a 3 times 3 to the 2n. I hope you're okay with breaking down that part. And from there, I'm going to bring out the 3 in the denominator, bring it in front of the sigma notation, become 1/3 because it's in the denominator. So I get 1/3 sigma n to the n, and the denominator I get 3 to the 2n, right? So I'm going to write as a 3 squared raised to the n. That's the same thing as 3 to the 2n. And the benefit, the reason I'm writing like this is that now I have this part raised to the power of n if we look at it together. So that will become 1/3 sigma n over 3 squared raised to the power of n. So now I have something raised to the power of n. When I apply the root test, the power n, this exponent will cancel with the nth root. So that's just the sort of the preparation work. So now let's try the root test. We're going to define L, which is the limit n goes to infinity, nth root. So this time I'm going to use this notation. I hope it's okay. Something raised to the 1 over n. And inside the nth root, it's just absolute value of an. An is n over 3 to the squared. So you can write 9. And then raised to the n. So that's the first step. That's in an absolute value sign. But now I'm going to move in the next step, I'm going to move the exponent and move it outside of the absolute value. So that will become the limit. Absolute value n over 9 raised to the n, and outside we have an nth root 1 over n. And then that becomes limit absolute value n over 9. Since n is always positive, so I'm just going to drop it doesn't matter now because we're almost at the end, right? N goes to infinity. We can just take the limit directly. If n goes to infinity, the numerator goes to infinity. The denominator is always 9. So this just going to go to infinity. If L goes to infinity, which is more than 1, right? Therefore, since L is greater than 1, that's what we found out. So if L is greater than 1, then the series is divergent. Therefore, the series, but which one is it? It's this one, right? That's the one that we focus on. There's a 1/3 in front of it, but it doesn't matter because 1/3 multiplied by a divergent series is still divergent. So therefore, the series n over 3 squared to the n is divergent. And if we multiply by 1/3, therefore, the original one, n to the n, 3 to the 1 plus 2n, which is equal to 1/3 of this divergent series n over 3 squared to the n, is also divergent. So that's the last example I went through. Any questions about this example to apply the root test? The process is really the same as the ratio test. I know both are new to you. I'm going to give you some homework problems after tomorrow, or probably before tomorrow, but it's not going to be due until next Thursday. So you can practice those tests. Any questions about this example?
Yeah, so I understand how we get the limit n goes to infinity to n over 9 to the nth power, but where do you get that 1 over n, like to the over like the entire
Oh, that is just so the 1 over n, this one. That's just a notation of nth root. So by definition, so let me I sort of change the notation here. So by definition, we define the limit. So sorry, we define L as limit n goes to infinity of nth root, absolute value an, which is what is an? N over 9 or n over 3 squared to the n. So that's a notation. Well, one of the notations to define L, right? But instead of using nth root, I use the parentheses 1 over n to replace nth root, but it's the same notation. I mean, different notation, same meaning.
So once we have the limit of n goes to infinity, n to the 9th to the n power, you're just able to apply that rule of the root. And okay. Yeah.
So that goes to infinity is more than 1. Therefore, the series is divergent. But that's a root test tell us. All right, any other questions? Like I said earlier, those two tests, the process of applying them is, it could be confusing, right? Because you get a lot of absolute value, roots, power, a lot of things going on. But actually the applying process is easy. You just have to be very careful with the algebra in the process. But be careful, sometimes you may not be able to make a conclusion, right? If it's equal to 1, if L equals 1 at the end, you cannot conclude. You have to use a different test to make the conclusion. Which is true with any test, right? You apply it, you may or may not be able to make a conclusion. All right, I'm going to stop there and let you ask questions. Anyone can go. There's no particular order there. Any questions about the homework? If not, maybe we can finish early. But I do want to give you a chance to ask questions. Oh, and also I want to point out that in homework 7, a lot of questions was basically just give you, convergence, divergence choice, right? So do not just click on them and try them, It's not trial and error problem. You have to understand, like let's say you, for some problem, you pick the answer that's convergent. You have to understand why is it convergent, right? You should be able to show the work. So do not just, click on one. If it doesn't work, click on the other one. That's not the purpose of the homework. So, okay, Chris, go ahead. Tell us what your question from the homework.
It's a sum from 7 to infinity.
7 to infinity.
Of n plus 5 over n plus 2 to the 6th.
This one?
Yep.
Okay. Yep. So this is a good question. So this is a homework question. It will be problem like this. I'm not saying this particular problem. Problem like this will be on the exam. But the stuff above it is not going to be on the exam. So for this one, I believe the best way to do is to use the limit comparison test. Let me think. And I think comparison test also works. Okay, so there's two ways. One is try the limit comparison test. One is the direct. So I'm going to try with the direct comparison test. So direct comparison test. So to do that, I'm just looking at the denominator. The denominator has n plus 2 to the 6, right? I know that n plus 2 to the 6th power is greater than or equal to n to the 6th power. You agree? Because if you add 2, then you raise to the 6th power, you get bigger, right? And but if it's in the denominator, so that means 1 over n plus 2 to the 6th is actually less than or equal to 1 over n to the 6th power. And if I have the same numerator, n plus 5 to the n plus 2 to the 6th, that's going to be less than or equal to n plus 5 over n to the 6th. So that's a direct comparison, right? If I make the denominator by dropping the positive 2, I end up with a smaller denominator, but the value gets bigger. So that means this given series, n plus 5 divided by n plus 2 to the 6th, is going to be less than or equal to the series n plus 5 over n to the 6th. I know that, right? And then the next part is to decide if this convergent or divergent. That one is simpler. We should be able to determine the convergence there. And to do that, I'm going to use a trick. So now we're going to look at this n plus 5 over n to the 6th power. I'm going to split it into two series. N over n to the 6th plus 5 series 5 over n to the 6th. I'm using so in this case I'm using the direct comparison test. So that's a question, why do we only worry about the denominator? I'm looking for a comparison test, so I'm trying to find a series that's simpler than the one given. Here, the numerator you add a 5, the denominator you add a 2 to n. So the quickest way to get a new fraction you can compare with a given an, right? It's you either drop a term in the numerator or you drop a term in the denominator. So what I did, I chose to drop the positive 2 in the denominator to give me a new fraction that's bigger than the given one. Therefore, the new series I got is bigger than the series that's given. So the first one is just 1 over n to the 5th power. The second one is 5 over n to the 6th power. And I hope that at this point you know well, not immediately, but at least you know how to determine if each one of them is convergent or not, right? This part and this part, they're all the same. I mean, the 5, you can move it in front. I should have done that. So 5 sigma 1 over n to the 6th. The first one is just 1 over n to the 5th. They're the same type because they are the form of 1 over n to the p. That we can use p series test. So use p series test. And if you do that, this is a p equals 5, right? This is a p equals 6. Both are greater than 1. Therefore, both are convergent. If the sum of two convergent series will be convergent in this case. So it's convergent here. If this bigger series is convergent, if we go back, the series that we found out is a bigger one, right? So this larger series is convergent. Therefore, there's the one that's smaller than it, the one that we're interested in. So this one is convergent. The one that we are interested in is smaller, so it has to be convergent as well. So that's using the direct comparison test.
So again, why did you use the denominator over the numerator? for like changing in terms of like something less than the fraction?
Remember that comparison test, you want to find functions that's bigger and smaller on both ends and to try them, right? So if you have n plus 5 over n plus 2 to the 6, the one that's definitely bigger than this one is you sort of manipulate the denominator by making it smaller. So if you make the denominator smaller, just n to the 6, that will be bigger than the given one. You could also manipulate the numerator, make the numerator smaller, that will be smaller than the given one. So if you just say n over n plus 2 to the 6, that's definitely smaller. That's a few other ones, right? 5 over n plus 2 to the 6 is also smaller. To make it bigger, I think if you just have 2 there, n plus 5 to the 2 to the 6, that's also bigger. But you kind of have to play with which one is the one that will be helpful. It turns out that this one is the most helpful one if you want to use the comparison test.
So I guess I'm just a little bit confused. Why did you like only use the denominator in your direct comparison test versus that when you had a numerator? Like, do you see what I'm saying? Like in your direct comparison test, you just had n plus 2 to the 6th power is greater than n to the 6th. Like you just completely didn't even include the numerator.
I just want to show where that come from, the reasoning. Why do I pick this? I want to show where that come from. It come from the idea by just looking at the denominator, you want to find a smaller denominator first, right? So that's what I did. I taking the denominator that's given, I found a smaller denominator n to the 6. And then if I make both of them the denominator, then the fraction, well, with a smaller denominator, is actually bigger. So those work I did in the beginning, those kind of like leading to this step to finding the correct fraction that will be bigger than the one that's given. So that's sort of like the process in my head. All right, so that's that question. So if you, like I said, if you by just looking at, some of you may be getting good at this, you might by just looking at that expression, you immediately see that you can use n plus 5 over n to the 6 as a comparison. That's totally fine. You don't have to show any other work, but just want to explain where that comes from, at least from my from what I see. All right, any other questions on this problem? All right, Aiden, you had a question.
Yeah. So what's the name of that symbol that's like the big capital E? Or backwards?
Sigma notation?
Yeah. So it's yeah, that, and then infinity on the top, n equals 1 on the bottom. And then it's 1 over 2 plus e to the negative n.
This one? Okay. So Jacob was asking why was the final answer convergent? Well, we used comparison test for the previous example, right? So for the one that I'm comparing with, the one in the green here, this is the one that I'm comparing. This one is the one that's given, right? The one in green, it's a lot easier to find out whether it's divergent by splitting it into 2 series. So I did, and I found out both series are convergent. Therefore, the one in green is convergent. right? That series is bigger than the one that's given, right? So if you have a larger series, the each term there is bigger than the one that's given and is convergent, which means the sum will be approaching a finite value, right? That's what being convergent basically means. So if the bigger series, the series of bigger values, the sum approach to a finite value, then the one that's the series that has smaller values also has to approach a finite value when you try to find the sum. That's just the comparison test, right? If you kind of, I always think about like if you have a bigger box that it has a finite volume, then if you put a smaller box inside, as long as you can fit inside, then the smaller box also has a finite volume. That's sort of the idea between comparison.
So if you had a smaller fraction in sigma notation and it was divergent, that means that they both would be divergent?
Correct. So on the side note, so just to repeat what Aiden said, so if you have two series, let's say AN, this is BN, if this one is divergent, then this one has to be divergent. And the earlier one, AN, is less than or equal to BN. So if this BN is convergent, the bigger one is convergent, then the smaller one has to be convergent. Otherwise, if you don't have this relationship, you cannot make any conclusion. Okay, good. So let me go to this question that Aiden asked. So if we have this 1/2 plus e to the minus n, right? So the first thing I'm going to do is I'm going to there's maybe other ways to do it, but I'm going to try the simpler one. I'm going to try the divergent test. And in fact, just based on experience and also based on the problem that I have done it before. So I'm going to try with divergence test. Let's see, divergence test. So this is AN. I'm going to take the limit of AN as n goes to infinity. And then that will be limit n goes to infinity of 1/2 plus e to the negative n. And as n goes to infinity, if you recall that, so just on a side note, so note limit n goes to infinity of e to the minus n, that's a limit n goes to infinity of 1/e to the n. If n goes to infinity, e to the n goes to infinity. That goes to 0, right? So as n goes to infinity, this part will approaching 0, and the overall value when we take the limit is approaching 1/2. And that tells you that it's not a 0. And if you recall for the divergence test, you compare the limit with 0. If it's not 0, it's actually a good thing. So the limit is not 0. Therefore, the series is divergent.
So I'm a little confused by that e to the negative n step because it's already in the denominator. Wouldn't you put it up in the numerator? Or am I wrong?
You don't have to put in the numerator because we're just taking the limit, right? So when we take the limit, we can take the limit of 1, which is 1. We take the limit of 2, which is 2. And then we take the limit of e to the negative n. You basically take the limit of individual terms. That will give you
But it wouldn't be 1/e to the negative n?
You can write it as 1/e to the, so you could, from here, you could write as limit 1 over 2 plus 1 over e to the n, right? And then again, you can just sort of basically, well, plug in quote notation, not really plug it in, right? You can just assuming that n is infinity, so that will give you 1 over 2 plus 1 over e to the infinity, which is again 1 over e to the infinity, which is, I should use the approximation. So that's a 2 plus 1 over infinity. 1 over infinity, again, that's a 0, right? Which is still going to be 1/2. If you didn't do that, you probably think, oh, why can I just somehow bring the e to the n to the numerator? Yes, you could, but if you do it correctly, you should end up with 1 over, so basically multiply common denominator in the denominator, so that's a 2e to the n plus 1 divided by e to the n, right? So that's a e to the n over 2e to the n plus 1. And take the limit, right? If that's what you are thinking, the next step, before we take the limit, we should divide by the leading term, which is e to the n to all terms. Again, that will take you back to what we had earlier in the beginning, sort of one step back. Doesn't really, move forward much. So that's a limit 1 over 2 plus 1 over e to the n. Then you take the limit as n goes to infinity. So that doesn't really help much. It's still taking you back to this step in order to take the limit. Can you do a p-series test where we have to manipulate the denominator and numerator? All right, Jacob, I don't have a particular example in my head, so you're gonna have to come up with the example or find the correct example, and we can look at it. So Aiden, did that help that problem? So again,
Yeah.
maybe I'm just lucky, right? By trying divergence test first. If I try comparison test, I probably, so take the given example. So if I want to try comparison test, the direct comparison test, 1 over 2 plus e to the negative n, I'm probably gonna, again, the denominator has the addition, has 2 terms. So I'm gonna drop one of them. I'm gonna drop the plus 2. So that's gonna be less than or equal to 1 over e to the negative n. And then just focus on this part. You can, again, for this series, you can try the divergence test, or you can try the integral test. I think integral test also works here, which is n from 1 to infinity. You can try divergence test or integral test, which is give you 1 to infinity, 1 over e to the minus x dx. And from there, you should be able to find out whether that's convergent or divergent.
So in terms of like the comparison one, you would find that 1 over e to the negative n, and then you try either the divergent or integral test, and that one down there that you just showed, that's the integral test?
Yes. So the integral test. And you can even just apply the integral test directly. I have to think, let me think a bit to see how complicated it is to do the integral. So suppose we're going to do the integral test directly. So that will be just integrating from 1 to infinity of 1 over 2 plus e to the minus x dx. I think it's manageable. You just call the denominator u, right? If you use u substitution. So that's the limit t goes to infinity, 1 to t, 1 over 2 e to the minus x dx. Oh, sorry, 2 plus. So if you just say, I'm going to let u equals the denominator, 1 plus e to the minus x, find du.
Are we just doing this problem a few different ways?
Yeah, I'm trying to think about a few different ways. I did not work out this integral test, so I don't know how complicated it is from there. So I'm going to stop there before I dig a bigger hole for myself. So I'm going to stop there. But I just want to show you, that you can try different ways. Some will work nicely, some doesn't.
So I just got a quick question before we move on to something else. If we were to try the divergent test, how would we do that? Would that be setting n to infinity and then trying that? Or what would we be doing?
Are you talking about here?
Yeah.
Okay, so divergence test, this is the an, right? You will be taking the limit as n goes to infinity of an, just like the very beginning when we try the divergence test immediately.
Okay.
And to see if that's going to be a finite value that's not zero.
Is there any test that you would like try first for the exam? Like, would you try the divergence test first on some of these, or like, I'm just trying to get kind of like started.
If you go to the book, which is the next section, 11.7. Let me just write down so if you look at it, you don't know what to do at all. Like, you just think about it, and then none of the tests like seem to be obviously useful. So you just go to 11. So you will be trying on 11.7, page 779. So page 779, section 11.9, sorry, 11.7. It gave you like a sort of strategy of how to do the testing. So the first one, usually the easiest one will be the divergence test. And then if you see something that you can use p-series test, use p-series test. And then if that doesn't work, look for some geometric series patterns. If you don't see that pattern, try comparison test. And so on. If not, maybe try integral test at the end. So it does have a list of tests that you can try. But for now, like I said, like the very beginning I wrote, we talk about divergence test, p-series test, integral test, comparison test. Just try with the divergence test and the p-series test first, because those are the simpler one. If that doesn't work, try the other one, the other two.
And the geometric series test will also be on the test?
Correct. That's just, just looking for the pattern, right? Like an A, R to the N. If you see this pattern, then that's a geometric series.
Okay, thank you.
Yep. All right, I think Sam has a question. I'll answer that first before I talk about the one from Jacob.
Yeah, mine was the summation of k equals 1 to infinity of k squared over k squared minus 4k plus 8.
This one?
Yeah.
Okay. So this one, if we, well, let's just kind of take a quick look, right? Any suggestions of which test should we try first for this example? Divergence test. So if you're good at this, if you try it before, and then well, let's just try with divergence test. So we're just gonna take this part, and then we're gonna take the limit of it as k goes to infinity in this case. So that will be k squared over k squared minus 4k plus 8. And that will be, we have seen this type of questions a few times, right? Just divide by k squared. And that should be pretty good in terms of getting to the limit. So the numerator just 1. The denominator is 1 minus 4 over k plus 8 over k squared. But as k goes to infinity, that just gives you 1, which is not 0, tell you that it's divergent.
Okay, that's exactly what I did, but I thought that I guess that I thought that was it was convergent and that was the sum. Could you maybe explain like how to tell the difference between that?
Can you say it again? It's
So I did exactly that, but I clicked convergent instead of divergent, and the sum was 1. Like that was my thoughts.
Oh, the sum is not 1. So this when we take the limit, we end up with 1. This value, because it's now not 0, so this value tells that the series, this series k squared minus 4k plus 8, it tells us that the series is divergent. It's not the value for the sum. So this 1 is not value for sum for the series of the sum. So we did not find the value for the sum. So if you kind of notice that for all those tests that when we do the test, we're not finding the values for the sum. We're just finding whether it's convergent or divergent. Even if it's convergent, we still did not find out whether it's, what the value we approached to. We did not do that.
Okay.
And if you want to know the sum, right, the easiest way at this point, so to find the sum, the actual sum, depends on that, depends on the series. This one is not geometric, so we cannot use the geometric series sum formula. So to find the sum, it's best if you kind of just, for now, finding the partial sum as 1, as 2, as 3, and so on. Try to see what the number is approaching to. If it's convergent, if it's divergent, just infinity.
And that's when you plug in like 1, 2, and 3 for the variables.
Yeah. So S1 will be just the first term. So we just put 1 square over 1 minus 4 plus 8. That's the first.
Okay.
S2 is you take 2 terms, add them together. So you got 1 over 1 minus 4 plus 8. Then you have to add the second term from the series, which is putting 2 there. And then the S3 is you take the 3 terms, you add them together. And then if it's convergent, you can see the value is approaching a number.
Okay.
So it's the answer you got is it's divergent because it's anything except 0, or is it anything greater than 0? That's telling us it's divergent.
Anything except 0.
Okay.
Yeah. If it's not 0, then it's divergent. When I say not zero, it could include infinity, right? If you take the limit, you end up getting infinity or negative infinity. That in that case, the limit is called, we could say the limit doesn't exist. It's also divergent. So if limit at the end equals infinity or negative infinity, it's also divergent. It's just not zero. All right, so Jacob has a question. So which is from sigma 1 to infinity, square root of n to the cube plus 1 divided by 3n cubed plus 4n squared plus 2. For this one, if we try to use the divergence test, it's probably not going to give us anything. I'm just thinking, because if we just take the limit as n goes to infinity, cube root, square root of n cubed plus 1 divided by 3n squared plus 4n squared plus 2. And if we, that's a cube, if we divide by n cubed, and in the numerator, because we have a square root, if we divide by n cubed, it's actually inside the root. So if you have a square root divided by n cubed, that's equivalent to square root divided by square root of n to the 6th power, right? I hope you agree with me on that part. And that is the same thing as a square root of whatever divided by n to the 6th. So when you divide by something that's not in the square root, when you put it in the square root, you have to increase the exponent by, sort of double the exponent. So in the square root, we're going to have to add n to the 6th. And then that becomes limit square root of 1 over n cubed plus 1 over n to the 6th divided by 3 plus 4 over n plus 2 over n cubed. If n goes to infinity, this term goes to 0, that term goes to 0, the whole numerator goes to 0. The denominator becomes 3. So that just becomes 0 over 3, just 0. Right, so the divergence test doesn't give us it's a divergent, doesn't tell us it's divergent. So this is the inconclusive. For this problem, I don't recommend using integral test. So integral test, if you write as 1 to infinity of square root of x cubed plus 1, 3x cubed plus 4x squared plus 2 dx, not easy to integrate, right? So not easy to integrate. So probably wouldn't try integral test here. Divergence test doesn't work. Integral test, not easy, probably very difficult. P-series test we cannot use. So this is not in the form of 1 over n to the p, and it's not easy to write in that form. So P-series test also doesn't work. And it's definitely not, it's not a geometric series, right? So you cannot, and it's also not in the form of a times r to the n. It doesn't work there. So those doesn't work. So what do we have left? Just comparison test, right? So comparison test at 2, that's a direct comparison test. That's also the limit comparison test. So for this one, the direct comparison test is also not going to work easily. So you can try it, but it's not easy to find a function that will be bigger than this or smaller than this and it works. So try limit comparison test, which is we have to take the given one. So we have to take this one. Let me just write down. I know we're running out of time, but I'll be done in 2 minutes, I think. That's the correct one. So in order to use a limit comparison test, we have to take this. I'm going to call it Bn, and then we have to find a second series that's simpler than this. And if you remember the example I did on this limit comparison test, the second series is coming, I use the one that's the leading term of the numerator and the leading term of the denominator of the given one. So I'm going to take square root of n cubed for the numerator by dropping the 1, and then 3n cubed for the denominator. Right? Yeah. So that will be my new series. So new series. And then this, I'm going to call it an. It doesn't matter which one is which. And for the limit comparison test, we need to define a C, which is the limit n goes to infinity of an over bn, I believe. Let me just double check because as you can see, I don't remember everything. And then we want to know if that we want to know the C value. So so from here we just plug in an and a bn. It turns out that it doesn't matter which one goes in the numerator. You can put bn in the numerator and an in the denominator. So that will become limit an, which is square root of n cubed, so that's the n to the 3/2. The denominator is 3n cubed, and then divide by the bn, which is square root of n cubed plus 1 divided by 3n cubed plus 4n squared plus 2. And then I'm going to flip the denominator. And the numerator, you can obviously simplify it, but let's just leave it for now. So that will be the numerator is n to the 3/2 divided by 3n cubed times 3n cubed plus 4n squared plus 2 divided by square root of n cubed plus 1. And I'm going to I'm going to simplify the fraction on the left. That's a limit 1 over 3, and the n to the 3/2 divided by n cubed. That's a 1 over n to the 3/2 times 3n cubed plus 4n squared plus 2 divided by square root of n cubed plus 1. And now I can combine the denominator. So that will be limit 1/3. I'm going to bring it outside because it doesn't matter. Doesn't get involved. The n to the 3/2, I'm going to combine with this. If you rewrite n to the 3/2, that's a square root of n cubed. So if you combine with the square root that's already there, move it down a bit. So that becomes square root of n to the 6 plus n cubed. And the numerator, you get 3n cubed plus 4n squared plus 2. And from here, I'm just going to divide by n cubed, because that's the leading term of the numerator as well as the leading term of the denominator, right? Because n to the 6 dominates the denominator in the root, and then when you take a square root, you get n cubed. In the numerator, I divide by n cubed. In the denominator, I also divide by n cubed, but when we put it inside the square root, it becomes n to the 6. So that will become 1/3 limit is 3 plus 4 over n plus 2 over n cubed divided by square root of 1 plus 1 over n cubed. As the n goes to infinity, those terms with the n in the denominator become 0. We end up with 1/3 times 3, which is 1. So C is 1. And if you go back to the limit comparison test, C, when we take the limit, we end up with 1. So C equals 1. And that does not tell you whether it's convergent or divergent. It only tells you that, so since C is 1, which is positive, and it's finite, which tells that both series, the one that I picked with AN and the one that I was given, the BN, both of them behave the same way. So both series are either going to be convergent or both are divergent. That's what this tell us.
What if it wasn't 1?
Say it again.
What if it was not 1?
It depends if it's so C has to be positive and finite in order for them both to be convergent and divergent. If it's negative, then we cannot conclude.
Okay.
Or if it's infinite, right, we cannot conclude. We just, so in order to make this statement both, so the C has to be positive and finite. So what is AN? AN is, let me just fill in, I got a square root of n cubed over 3 n cubed. So that's what AN. BN is the one that I'm looking for, which is a square root of n cubed plus 1 over 3 n cubed plus minus plus, I forgot, I think it's a plus 4n squared plus 2. Right, so both of them are convergent or both of them are divergent. That's what this limit comparison test tells us. But can we work with a simpler one and to see if it's convergent or divergent? We should be able to, right? Because if we take this one, we simplify this fraction, so that becomes, I think I did it already. So that's a n to the 3/2 divided by 3n cubed. So that's a 1 over 3, 1 over n to the 3/2. I think that's what I did earlier. And from here, for this simpler series, the 1/3 you can bring outside. You get 1 over n to the 3/2. And in this series, you can apply the P series test, which is P equals 3/2, right? So that tells you that's greater than 1, so it's convergent. Which means that this part is this series that I picked by using the leading terms of denominator and numerator. So that's convergent. Since both are convergent, therefore this one I'm looking for is also convergent. It takes a long way to reach the conclusion. That's sort of the disadvantage of this test. It does work.
I understand the final answer. How did you split up the n to the 3 over 2 divided by 3 to the n third?
How did I split this?
Yeah.
Yeah. So what I did is the 1/3, the 3 in the denominator, I just put it aside, make it 1/3. So I get 1/3, and then I have n to the 3/2 divided by n cubed, right? And then for those two n terms, I subtract. So when you divide the terms with the same base, different exponent, you subtract. So that's n to the 3/2 minus 3 in the numerator. So that becomes 1/3 n to the negative 3/2, right? 3/2 minus 3. And then that's 1/3 1 over n to the 3/2.
Okay, thank you so much.
Yep, no problem. All right, it's 8:01. I'm gonna let you go. I know that some of you still have questions. So perhaps ask them during office hours tomorrow, and before the exam, I'm gonna spend about 20 to half an hour, 20 minutes to 30 minutes to go over final questions. All right.